What's up, everyone? Welcome back to Better Biomed. Folks, today we're going to cover another complex topic, and it's one that I believe if you're going to be in advanced level biomed, probably even with medical imaging, this is probably something you should understand, and it's electronics communications. See, devices have all sorts of components, and they have to talk to each other. Especially when you get into complex medical devices, you got boards, etc., that are talking to each other. And you might be trading out a board that might not even be bad. And the default Biomed thing is the like reseat connections and stuff. And, you know, we are technicians. We can go in and we can test this stuff. And I'm going to show you what you should be looking for and the types of protocols that we might be dealing with. Let's do it. So here we go, guys. Advanced Biomed, electronics, communications. This is a rough estimate of all the different items that are going to be located inside your cell phone. And believe it or not, almost every one of these components has some sort of its own controller, and it sends and receives data from the main processor. And in order to do that, it has to have a type of protocol, and they have to know how to talk to each other. And, you know, sensors and stuff, they might always be streaming, or they only might send data when it's requested. Interesting. So your cell phone has quite a bit. We got microphones, accelerometers, humidity sensors, CMOS, imaging. We got gyroscopes, magnetometers, fingerprints. I don't see NFC in there. And that's another one. Temperature sensor, pressure sensor, touch sensor. There's a lot of sensors. You know, we got the biometric sensors in there. I don't think I see the camera on there. There's a CMOS imager. I guess that's it. But anyway, there's a lot of stuff going on your cell phone. And what's even crazier is all those little data passageways are exchanging data nearly at the speed of light. And it's a crazy amount of data that's going back and forth inside this little device. And more so, we've got other little components that are also trading data like lightning fast. And one of the things you're going to realize is a lot of biomeds out there say, oh, when was the last time you had to get on an oscilloscope? And I've actually heard the conjecture that oscilloscopes are overrated and they're not really needed anymore. Wrong. Absolutely wrong. Guys, I did another video on the generations of electronics and how we are moving more and more so towards this kind of stuff here. While it is like replace it type of stuff, nonetheless, there are boards and whatnot that you can figure out if they're talking or not talking, and you can be a little bit more accurate on coming to find what the problem is. I mean, your troubleshooting can greatly be improved by understanding how things communicate. All right. This is a chart of a coffee pot. Believe it or not, guys, coffee pot. And let's just take a look at some of this stuff here. We have a power supply. We got a motor controller, system control, which is probably the main CPU, user interface, which often the user interface does have its own little CPU in itself. We got sensors, we got connectivity, because, you know, we got Wi-Fi and all that in coffee pots nowadays. And security, I guess you'd have to have some level of security, right? Then we got over here on the motor controller, we got a gate driver and a 3-phase inverter for the motor. Somebody's got a brushless motor on their coffee pot. Good for you. That's an expensive coffee pot. And now down here we have inverterized milk frother. Now, in order to drive these MOSFETs right here, yeah, you got it. These things have to talk. And it's not going to drive the milk frother unless it's got input from sensors saying, hey, it's safe. And while it's driving the motor down here, notice we have a position sensor and a current sensor. It's monitoring to make sure that that motor is, first off, moving in the correct direction, because motors can move in 2 different directions, right? And then it's also looking to see how long it's been running. It's got a timer and is measuring the amount of current to make sure that that motor's not froze up. Since this right here is on a coffee grinder, it's possible that something ends up in the coffee grinder that shouldn't have been in there, and it could what? It could lock up a motor. And motors, when they're completely froze up, that's when they draw the most amount of current, and that is a protection system. Pretty cool, huh? That's right. All those items have to communicate. this kind of brings it all back to us, guys. And I've got right here upstream pressure sensor. We got stepper motors. We've got encoders. We got apparently a different slide. We got LCD touchscreen. We got buttons, USB, Wi-Fi, battery cells. That's right. Batteries are smart. They talk now and they say whether or not they're good, the amount of charges they've had on them. They got serial numbers now. It's crazy. We got a downstream pressure sensor, ultrasonic air bubble. We got a locking bar position sensor to make sure it's in home position or not. We have a temperature sensor. We've got stepper motors. Again, stepper motors. They not only can tell what direction they're going, how far they've gone because of the amount of pulses, but they can monitor current and they can tell whether or not it's froze up. It's pretty cool because if the occlusion's too high, that's one way of finding out, is by the current for the motor. And then over here, I got another stepper for the peristaltic pump itself. Interesting. Upstream pressure sensor. Okay. So all these items here in a regular infusion pump, that is a lot of stuff going on in an infusion pump. And guess what? They all communicate. We're going to talk today about how they might be communicating to this MCU right here, which is the main computer unit or whatever they want to call it. But that's right. We're going to talk about that next. So guys, when devices talk, it used to be back in the day that they had this stuff called parallel. PATA, P-A-T-A, but we just call it parallel. And parallel is this picture over here on the left. It sends like 8 bits out all at once for one clock cycle. You see right down here. The clock pulses and it goes, here's my data. And then the problem is then you'd run into bottlenecks, right? Because your receiver, then you'd have to take that data, you'd have to throw it into memory and or send it over to the CPU and figure out what to do with it. And that was for one clock cycle. So yeah, you could get data, but then what do you do with it, right? You only got like 2 hands, right? Think about it that way. So what's going on is all these balls are coming in, you grab them, and then you're like, okay, this one goes over here, this one goes over here, this one goes over here. But then we had serial. And you can see over here, this is a serial interface. Notice we got all these clock pulses. Bop, 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 bop. It's very constant and it's very measured. Your clock pulse is when it's going to transmit data. Like, here's one, here's one, here's one, here's one. And every time there's a clock pulse, it sends out 1 bit. So instead of sending out 7 bits or 8 bits with the parallel, now we have 8 bits over a period of time. And guess what? As time went on, we got better at serial communications and they've only gotten exponentially faster. So instead of like having your hands full of all these data bits and trying to figure out where they got to go to, and that being the bottleneck, we've just gotten so much better at dishing them out really fast. Okay? So almost everything nowadays is serial because we are so good at it right now. And it's incredibly fast. Data rates are just gigabits per second. It's crazy fast. So when devices communicate, they're either going to be synchronous or asynchronous. Synchronous is exactly what we just talked about right here. You got one clock pulse, one data with serial. With parallel, obviously we just said 8. You wait for the clock pulse and then you send it or receive it, one or the other. With asynchronous, it's a little bit different. They have stop bits and they have start bits. And most importantly, when you have asynchronous data, you have to have the correct baud rate. You've probably all heard that back in the day of modems. Remember modems? When you call somebody, you hear the that sound, all that noise was the handshake where they're saying, hey, this is how fast I can talk. How fast can you go? And it says, okay, I can go that fast. Let's talk it that fast. And they handshake, right? Well, asynchronous, usually you have to set the baud rate. It's not normally detectable, or if it is detectable, you want to make sure that it's configured correctly, because if one's talking too fast, it's going to be gibberish, okay? So with asynchronous, it's very important that we get the same baud rate on both devices. That way they can talk. Sync clocks control data transfer rates. All right, so we just talked about synchronous, and many, if not most things nowadays are going to be synchronous. Not everything, but many things are. And what happens is when the clock pulse goes high, it sends data, right? And this right here is a period from this point to this point when the next wave starts. That's a period. And you can see right here, that creates a binary 1. So it says, okay, for this clock pulse, it went high, that's a 1. And then the next period, look at this. It's nothing, so it registers as a 0. Then the next one registers as a 0. Then the next one registers as a 0. And then guess what? We're on the 4th or 5th clock pulse, and on the 5th one, data goes high, which is, what, 3 volts, 5 volts, whatever. And now the CPU says, aha, that's a 1, okay? And then over the next 3 clock pulses here, notice it says, that's a 1, that's a 1, that's a 1. So it uses the clock pulses to figure out at that second or that millisecond, what am I? Do I have voltage or do I not? But as we're going to talk about later, it's not always the case, because some of them will drive the pulse low on the clock, okay? So don't always think that a binary is a positive value, because it could be a negative value, or it could be both. But anyway, 1 clock pulse, 1 bit, and that was the standard data rate, right? 1 clock pulse, all the devices that are connected on that receive that clock pulse, they all exchange data. And then the next pulse, and then they all exchange data. And then the next one, and the next one, and the next one, okay? And then somebody said, why are we only sending data on the rising edge? See right here? This is called the rising edge. This is the falling edge of a clock pulse. You can see it down here. And when they figured out, hey, you know something? You're right. There's 2 different state changes. A state change is when it, changes from 0 to 1 or 0 volts to 5 volts or 3 volts or whatever. There's 2 state changes for 1 clock pulse. Why don't we send data on the first point, and then on the falling edge, let's do it again? And that's what they did. And that's called DDR. Or, as you guys have probably heard, double data rate. How original, right? So there you have it. That's double data rate. It's on the rising edge and on the falling edge of every clock pulse. There's data that's changing hands. And believe it or not, now I think we have 4 state. So in the half pulse, it's doing something as well. So I don't know how that really works, to be honest with you guys, but we do have 4 state or quad data rate. So it's on the rising edge, on the plateau, on the falling edge, on the plateau, on the rising edge, the plateau, the falling edge, plateau. Okay, and that's quad rate, and it just gets crazier from there. Okay, but just know that data is normally changed on the rising edge, or the falling edge, or on the plateau. There's one part of the wave that everything knows to look for. And you can also set what that is. And you're also, if you use oscilloscopes, you can trigger on the rising edge, on the falling edge, on the plateau, or whatever. That way there you can see what data am I getting on this pulse. Yeah, it's pretty cool. So anyway, guys, that is data rates, and they are affected by the clock pulse. And over time, guess what? The clock has gotten faster. When you hear about your CPU that's a 3 gigahertz CPU, what do you think they're talking about? The clock rate. It can handle 3,000 times a second, or 3 million times per second. That's just incredible. 3 megahertz, that's what, 3 million times a second or whatever? It's just incredible how fast that stuff is just flying back and forth. So when you hear megahertz or gigahertz or whatever, that is the amount of pulses. That data is just changing hands. So let's talk about serial communications, because most of the stuff out there that you and I interact with is going to be serial. If you look over here, we got another one there. So let's start with the basics one. All right. USB, universal serial bus, right? Go figure. PCI Express, we got SATA, serial ATA, we got HDMI. Now, believe it or not, I did not know that HDMI was a serial bus, because it's got so many conductors in there that I thought that it might be in part parallel, but no, it's just really high frequency serial. Okay, we got I squared C. It says I2C, but it's I squared C. And then we got SPI, and the oldie but goodie, UART. UART, we know as serial. When you see like a serial port and a serial cable, that's UART, okay? And believe it or not, UART ports are all over the place to this day. In fact, I think I have one right here. I believe I can fly. I believe I have one right here. So this is a board for, apparently an out of focus board. This is a board for a, Philips Respironics. Yeah. And look right here. I got one little header right here, and I've got another one right here. We'll talk about that in a little bit. But that looks to me, especially that one, looks like a UART header. And UART headers are used for programming things or talking to things or doing debugging. So some cool stuff you can do by connecting or soldering into those leads right there. And then you can go on a terminal program on your computer. You can actually see what that device is doing. Or some of them are unlocked. You can actually give it commands to do other cool things. So UART hacking is pretty cool. That's traditional RS-232 serial. Okay? Let's talk about that UART. All right? So universal asynchronous receiver transmitter. And it's kind of simple, to be honest. Now, there's going to be a growing trend on all these communications, and that is this line right down here. You see that? Ground. On almost every single one of these devices, they have to, these communication protocols have to have a common ground. The ground has to be the same, because if you're going to send a data bit, which is what? It's usually a pulse, right? And a pulse is a voltage, right? Well, in order to send a voltage, you have to have a ground or a negative. So, in other words, without one, you can't have the other, because this means nothing if you're not measuring it against something. So, for UART, the one device has got a TX and an RX, and then the second device has got a TX and an RX, but you have to cross the lines. So on one device, the transmit pin, TX, has to go to the receive pin on the other device. So you have to make sure to cross those lines, as you can see here, the orange and the blue. And the ground has to be intact, because if it's not, that plus and negative doesn't mean anything, okay? And plus, the ground usually keeps the signal noise down, because any long conductor, actually any conductor, it doesn't have to be that long, right? Size doesn't matter, right, ladies? Any conductor out there can and will be an antenna, and it will conduct electricity and noise, and the ground is usually a shielded cable, and that will help keep the noise down, because it dissipates the noise to ground. All right, so that's UART, and here is that little UART jack I just pointed out to you over here on the Respironics board, and it looks just like that, okay? Now this one is a little bit different than what I've seen on many of them. Normally, the edge pin, either this pin or this pin, is ground. Luckily, it's labeled here. And you can kind of figure out what's ground and what's not on this one. You see this large bit of green right here? If I see a large bit of green, I'm normally thinking that's the ground plane on a board. And that is going to be connected to your pin, and I would normally think that that is going to be ground. But notice it says VCC. VCC is your positive voltage. And so you got VCC, ground, RX, and TX. Now you don't have to connect anything to VCC usually for UART. Normally it's just 3 wires, ground, RX, and TX. But notice right here, we have an inductor, we have some coupling capacitors, and it goes up here to power some other things. This is your positive voltage rail, whatever it is. And since it's on UART, I would assume that that is what, a 5-volt rail, I guess. And it only makes sense also because look right here. Here is your capacitor. And notice this side right here, your electrolytic, it's white. That means that you're negative. This over here is your positive, and it goes right here to that inductor and that controller. And of course, it actually might be a voltage regulator. So that is your positive voltage rail. So you can measure right here to right here. See this large bit of green right here? That is your ground. And notice how it also wraps around these pins and comes down here. And it goes all down here to the negative. That's right. So just pay attention when you see these little junctions between the via. That's called a via, the hole that goes through a board. That little junction right there to the surrounding solder mask, that means that that is ground, okay? But notice on this one, I told you the edge one is normally going to be ground. This one here, I'm really kind of confused by this because normally the square pin, like I have right here, normally the square pin goes to ground. In fact, hold on, let me see if I can get you guys a better view. And I got my fancy dancy microscope here. Let's do this. Let's do this. All right, let's see if I can pull that up for you guys. Okay, here we go. All right, folks, so this is my fancy dancy microscope. So we can zoom in and I can show you those headers that we talked about earlier. And right here is the edge of my display. And one of these really looks like UART and the other one, maybe not. The square pin that I mentioned, see right here how it's connected to the solder mask and the edge. And look at this guy. That guy right there really looks like that one's ground. It's got a little connection right here that goes to all this plane right here, all this up here, all this right here. So that is almost definitely ground. And then this one over here is VCC, but it doesn't really look like it's connected to anything. But guess what? I already said that for UART, you don't necessarily need VCC. So now you just got to figure out which one of these is the TX and RX and what the baud rate is, because UART is asynchronous. That means there is no clock signal. You just have the RX and TX, and you're relying on that baud rate to tell you what's going on. So notice how these two right here have a tiny, tiny little wire. See that little connection right there and that little connection that goes all the way up there? Those are almost definitely going to be RX and TX. And this guy over here, I see a connection to this guy, not to this guy, and this guy here looks like it's ground. That might be some other type of programming port. I would say this one here is UART. So guys, these type of things are all over the place. Right here is the backside. You can see what it looks like. You can also see how it's connected to this large plane right here, which is the ground plane. And here are those other two vias that are the RX and TX. Now this one over here, I could be wrong because look at this. It goes over here by this controller chip, and the other one comes over here to a capacitor and over here. This one here might be for these pressure sensors. You see that? So if that's the controller for these pressure sensors, maybe if you're programming it, maybe to also calibrate it, because you have to set the gain levels for these sensors. It could be that you calibrate this guy right here and store some settings. I don't know. I haven't looked up this chip to see what it is. But we got this guy and this guy. And if that there is a UART header, then that's almost definitely what those are for. So there you have it. All right. Well, all right, guys. So, UART, they are absolutely everywhere. In fact, I've got probably a couple of them over here on these components. Just be knowledgeable that it is possible to get in there and communicate on those, and it is a regular serial bus. Okay. And it's also the oldest. It is the oldest style bus that's out there. Okay. Let's talk about I2C or I squared C. That's inter-integrated circuit. And this is used for short distance communications like sensors in a cell phone. You know, they gotta talk, but not over very long distances. I squared C is fantastic for this kind of stuff, okay? And this is going to be a master and slave relationship. You see this? So we have the master, and the master tells everybody else what's going to happen, okay? And these are all the slave devices, and it's a bus. It's all in its own little like network, okay? And there are two wires. We have SDA, that's serial data, and then the other one is SCL, which is serial clock. So we have one that's data and one that's clock. And then we have two resistors. These are pull-up resistors, guys, for open collector, open drain. So when this bus is not doing anything, this right here, these lines will be high, right? They should be sitting at VCC. But when I2C starts up, they pull it low. They pull it to ground. So if these lines, if you ever see an I squared C line and you put your oscilloscope probe on there and you start a device up and it stays high the whole time, that means your master and or your slaves, none of them are talking. Nothing's going on. And notice how there's no clock, okay? There's no clock on this one. Oh yeah, there is. There's the serial clock. So the other thing about this I squared C is we have a data line, we have a clock line, we have a VCC pin, so it does have some sort of voltage that's required for this one, and then there's ground. And I already said earlier that all these devices right here, they have to share the same ground, which fortunately, if you're talking about in the body of a cell phone or whatnot, you're all going to have the same negative plane, right? Like I showed on the circuit board, you have the ground plane, which is usually the outer largest area of a circuit board. That is usually your ground plane, and they're all connected to it. And that's really unique because that means that they can communicate technically with only a VCC wire. So here we go. We got the master, we got these slaves. Notice how each of the slaves has their own address. Now the master also has an address, which is odd that they don't show it on here. But say this one right here, 1101001, and then this one here, and then this one here. So what it does is on the clock, remember on the clock, that's when they all share data, right? So what happens is the master will pull the clock and the data low at the beginning, and that gives him or her control over the bus, and everybody else shuts up, right? Says, hey, I'm talking here. And then everybody else shuts up. And that's when it says 1101001, here's for you. And then it's 10011000, this is for you, and this for you, and this for you. So an address is given, and then the data goes across. And then of course you have your two pull-up resistors right here, right? So at each of these slave devices, if the line is not in use, you should see it at each one of these pins on all these devices. You should see it pulled high. And we'll see that in the next one. So right here, you can see this is the communication process for it. So here we have open drain. It starts high, which means everything's got power. Everything, the chips all have power. And then when it starts, it pulls first the data line, then the clock. So by pulling the data line and then the clock, everybody else shuts up. And then first thing it does, it sends the address of the one it wants to talk to. So I'm not going to repeat that address because that 10111 whatever, that's a little bit crazy. But so it sends the address and then it says what it wants to do. It says 10001, I want to read from you. So it says read or write, and then the ACK is the acknowledgement where it says, yeah, okay. And then it then sends whatever it was asked for, and then it says, okay. Again, so there's always the acknowledgement, like, I want you to do this for me, and then it says, okay. And then it sends the data, it says, okay, I did it. And then what happens? At the stop condition, it pulls both those lines high again, because open drain, open collector, if nothing's transmitting, that line always sits at high, whatever high is. It could be 3 volts, could be 5 volts, etc. So the interesting thing about I2C is that not every device has to have the same VCC, because it's communicating over lows by pulling it low. High could be anything over like 3 volts. So whatever it is, it could be 3 volts, 5 volts, whatever. They usually don't care because it's only looking for the lows. However, if you have a controller, a master device that is like 3.3 volt logic, well, if you shoot 5 volt high back at it, you know, from one of the slave devices, you could damage it. Just to let you know. How do I know that? Well, because I got a couple dead Arduinos around here. But anyway, that's the rough communication process right there. So start condition, it says who it wants to talk to, what it's gonna do, read or write, acknowledgement. It's gonna send that, acknowledge, and then it opens it back up again. So what do you do if more than one device on your network has the same address? Well, that's going to create some problems. It's definitely going to create problems. Usually, every device on an I2C network has to have a unique address. Now notice the positive and negatives right here on this breadboard. Notice how they're all being shared. This device shares the same rail. These are power rails right here. So black right here is the negative. This right here is the positive. Same on this side. And this jumper is bringing the power over to this side right here. So they're all sharing the same positive and negative, but they all have different data lines. See that? Just a little pointer. And right here you can see the controller. This is actually the Arduino controller. This one's got an address, and then all 4 of these, they have address. So by having the same address on all these LEDs right here, they're all going to display the same thing. That's basically it. So if I have an LED display, like this guy right here, if this is an I2C display, and I have a second one next to it, and I keep both their addresses the same, guess what? They're both going to display the exact same information. So that's what they're portraying right here in this image, is that if, you know, you set out that you want half the reds and half the greens lit up, well, guess what? They're all going to be identical because they all have the same address. Now, I2C is one of the most common for sure when we have communications taking place within devices. But we also have something called SPI, or Serial Peripheral Interface. And believe it or not, SPI has also been like, it's been around since the 80s. But the cool thing is SPI, we probably all know SPI mostly from like video game controllers, you know, Serial Peripheral Interface. Well, guess what? A controller is a peripheral. And SPI refers to any of the slave devices as a peripheral. Although it could be like this display or something could be SPI, it still considers it a peripheral because the CPU is also, it's always the master. Just to let you know. So it doesn't necessarily mean something connected by a cable. A peripheral is just something else that's not the CPU. So on SPI, it's really unique. So we have a clock signal again. And here you can see it's MOSI and MISO. So that's master out, slave in. And then MISO is master in, slave out. But unlike the regular RS-232, you remember when we had to cross the lines, This time they actually got smart and they know what's going to be the master and what's going to be the slave. So if you have like this little battery controller right here, this guy right here is never going to be the master, right? The board by design is never going to be a master because it's just a stupid battery controller. So it's always going to be a slave. So they'll screen print on there, usually the MISO and MOSI, so that anything that's got a CPU is going to be the master out, and anything that's going to be this guy right here is going to be the slave, okay? So we have a MOSI, MISO. They do call them other things, by the way. They don't always call them those two things, but that's what I've experienced. That's what they call them. And then notice down here how we have the SSO, the SS1, SS2. Those are chip selects. What's chip select? We've never talked about chip select before. Chip select is almost like in one of the previous versions, one of the other protocols. Remember when we said that it will send out an address like on I2C that says, hey, you 11311442 whatever. It's going to give an address and then it says, hey, I want you to do this. This one here, all it does is it activates the chip select, which is normally just a conductor. As soon as it sees a signal on that chip select, it says, hey, you, I'm talking to you. So this interface right here, it's not the nice and neat bus that we've seen on some of the other protocols, but with the little chip select, it is actually kind of fast, okay? So we have 4 different pins required for the SPI, and on the master, it could have a whole bunch of pins depending on how many devices it needs to talk to. Because remember, every single one of these pins is going to be a chip select. See? This one goes to this one. This one here goes to this one. This one here goes to this one. Cool stuff, huh? So let's talk about the SPI protocol and how does it work, all right? So this is a synchronous data protocol. So it's going to send data with every clock pulse. See that? Boop, 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 boop. And right here, look at this, chip select. So it, again, open collector, open drain, stays high. And then when it wants to do something, it goes low. And then it starts the clock. You see how the clock isn't started right here? So it sends chip select low, starts the clock, and then this is a different look, isn't it? Look at this MOSI and MISO. See how the data is like interwound right there? These are data packets. So it's going to be master out. The master is going to send its data. It's going to be like, here, this is for you. And then remember, the chip select is talking to only one device at that moment. And then that slave is going to be like, here, I have this for you. And they exchange. And that's how it works with those 4. So the cool thing is we can see all this going on if we use an oscilloscope, especially an oscilloscope that's got like 4 channels. Again, you'll see these almost identical patterns up there on the oscilloscope. You can verify function. CAN bus. Believe it or not, CAN bus is probably one of the ones you interface with a lot every day and you don't even realize it. That's controlled area network. CAN bus is a really special one. It's used all over in industrial environments and commercial environments when things have to talk over a long distance. But they also use it in a place that you wouldn't figure. Cars. So your vehicle is got a CAN bus operating in it, and we'll talk about that in a minute. But this is how it works. You have all these different devices, and they have a low line and a high line. You see that? A low and a high. And the data is, it's either, I don't want to say nothing, but it's measuring the differences between the high and the low. So it's like either low or high. Notice both of them are moving. It's not one moving up and down. It's, we'll see that in just a moment. But so we have a high line, low line, and that creates some security and also some safety when it comes to noise, believe it or not, which is why CAN is used in cars. So let's look at all the sensors. Well, this depends on the car. Cars have way more sensors than this. But CAN buses also have like computers all over them. So your MAF sensor might be connected to like an emissions controller or something. Your NOx sensor just the same. We got ignition coil, VVT, variable valve timing. We've got fuel injector, throttle positioning. We got, well, the check valves. Those stupid things aren't. But anyway, you get the point. Is all these systems in here, even your seats and stuff, they have like a seat controller. You know, door locks. All these devices have to talk, and that's how they do it. And you know, it's kind of annoying that we have all these computers in cars, you know, the old timer thing. Oh, back when I had car, it never did all this. But how often do we now go long times between like heavy services? Couldn't do that with older cars. The reliability of modern day cars is actually way higher than the reliability on older cars, because there's a lot of things that we can automatically manipulate using sensor data that we used to have to account for manually. Things like the variable valve timing and whatnot. We can account for even things like emissions and or knock for if you're using the incorrect grade of fuel. We can now automatically adjust the engine for that without blowing the engine up. It's pretty cool stuff. You won't get the same amount of power, but it usually won't blow up the engine. That's all because all these devices talk to each other. Everybody that's ever received a check engine light, you know what I'm talking about. Well, that's what's going on, okay? When one of the computers out there says, guys, got a problem, that's when check engine light comes out, right? And you have to go and get it taken care of. So there you have it. Cars, CAN bus, they're all over inside cars. It's incredible. So a CAN bus signal. I told you earlier that the signal is a high and a low. And what they do is they move together. Okay? And you can see it right here. Now, let's say that there's some noise, all right? We have right here between the low threshold and the neutral threshold, we have what, 1.25 volts? That's nothing, guys. 1.25 volts is so low. So let's say we get a spike of noise in your car. Right here on this CAN bus low, and that spike right here, if you got two wires, guess what? They're both going to receive the same amount of noise, because if you got two wires on a bus, they're next to each other. It's not magic. The noise affects both of them equally. So we'd see a spike up here and a spike down here. But guess what? CAN bus is measuring the voltage difference between the high and the low. It's not measuring the high. It's measuring the difference. So when they're close together, it's a 0 digitally. When they're farther apart, it's a 1. And you can actually see that down here, the driver logic. So when they're far apart, it's saying, okay, this I recognize as a 1. This one here I recognize as a 0. This is a 1. And if there's a spike on this one and this one, that spike is going to be reflected on both of them, so that voltage difference doesn't change, right? When those two wires are going like this, and that spike happens, that spike is going to affect both of them equally, so we don't get any misreads and maybe cause a major situation. Because the last thing you want is your car to misinterpret data, right? So that is why cars are relatively unaffected by things like power transmission lines, other than like a nuclear blast. Like your car is normally going to keep running because they're designed so well for signal integrity. And anyway, guys, that is a rough look at communications, okay? I know this is some pretty high level look, and I know I'm just being very generic when I talk about this stuff, but you should know that oscilloscopes are still a practical tool that we can use to this day to help diagnose some of this stuff. I'm not asking you to interpret the ones and zeros, but if you can verify that you're getting transmission on certain wires and you know what those patterns should look like normally, then your troubleshooting skills are going to go through the roof. Okay? So that's my main objective here, is to make sure that you guys understand a little bit more about these little devices that you interact with every single day, as you should if you're a true technician. Thanks for watching, guys. I'm here to help you guys with any of your test equipment needs. Whether you need a quote or you just have a question about functionality, it's no problem. Just go ahead and shoot me an email at jbarber@bcgroupinternational.com or justin@betterbiomed.com. It's my pleasure to help you.